Hi, this is Pete Singer with Semiconductor Digest, and I'm talking to Mohamed Saleem, who is the CTO of Brooks Instrument. Hello, Mohamed, how are you?
Good, Pete, how are you?
Great. So you've recently introduced a differential pressure sensor based MFC, and I wondered if you could explain a little bit about the Brooks approach.
Yeah, absolutely. So let me talk about how the pressure-based MFCs operate in general so that you get a good idea of what we are trying to do here. So the pressure-based MFCs in general use a defined flow restriction to create a pressure drop in response to gas flow that is measured and utilize measurements of temperature, pressure upstream, pressure downstream in computation of flow. So by knowing the fluid properties and the geometries of the flow restriction, classic fluid mechanics principles can be used to determine the mass flow rate. So the conventional pressure-based MFCs use two discrete pressure transducers and to measure the pressure drop across a flow restrictor. So one of the drawbacks for this approach is the pressure transducers need to be precisely calibrated and matched. Otherwise, you're going to have problems related to drift and flow errors in the field. At Brooks, we used a unique patented approach to the design whereby we use a combination of absolute pressure transducer and a differential pressure transducer to measure the pressure drop across a flow restrictor. Now, the use of the differential pressure transducer eliminates need for matched and precisely calibrated pressure transducers to be installed in the pressure-based MFC. In addition, our approach is designed such that it works really well at vacuum conditions and also at pressure conditions that are above atmospheric pressure. The conventional pressure-based MFCs generally work in vacuum conditions, typically less than 400 torr. So by using this approach, we have extended the application of pressure-based MFCs, not only in dry etch, but also in deposition applications, which sometimes operate above atmospheric conditions. So that is, in a nutshell, our design approach.
And how do you see the semiconductor industry using these? Is it primarily for those applications you just mentioned, the etch and deposition, or are there particular gases or pressure ranges where they would be used?
Yeah, so some of the benefits with this approach is, as I mentioned before, it enables customers to use these MFCs for dry etch applications as well as chemical vapor deposition, which constitute majority of the process applications, right? So that's a significant benefit that we can get. But also our design approach enables, flow measurement of low vapor pressure gases. As you know, low vapor pressure gases are used a lot in a dry etch process. There are gases such as SiCl4, silicon tetrachloride, C4F6, C4F8. All of those gases are are significantly used in the dry etch processes. And these are all the gases that present significant challenges, especially when you try to have low flow process recipe steps. So with our approach, we can actually use low vapor pressure gases without any issues. Some of the other benefits that we have is that by positioning the control valve downstream of the flow restrictor, our devices are essentially immune to downstream pressure fluctuations, in addition to the upstream pressure fluctuations. So we have tackled both upstream and downstream pressure sensitivity issues with this design approach. And lastly, we are also able to get faster response times with our design approach, which enables us to position these devices for some of the cutting edge processes like atomic layer deposition, atomic layer etching, and so forth.
Okay. And of course, the semiconductor industry loves to talk about roadmaps, and there seems to be a roadmap for everything. Is there a roadmap for the MFC
yes.
technology?
Yes. So as I said, we are transitioning towards sub 3 nanometer process nodes. Our customers are constantly driving applications in these nodes. So that requires a very stringent specifications for mass flow controllers. So at Brooks, we are focused on continuous innovation. We are working on meeting these types of requirements. Some of these requirements could be wide turn down ratio for flow, with excellent accuracy and excellent repeatability, both at the low flow and the high flow regimes. So that's a significant requirement that is imposed on us by our customers. And in addition to that, our customers are requiring us to have ultra fast response times, typically less than 50 milliseconds for both turn on and turn off process steps. And these are typically used in pulse deposition and pulse etching, as I mentioned earlier, with respect to the ALD, ALE processes. And as you transition down to less than 3 nanometers, your flow requirements are shrinking, especially for dry etch, right? You're trying to etch, nanometer level features on the wafer. So that means you have to flow, less than 1 SCCM. You're talking about a few molecules of gas. So your mass flow controllers need to be able to measure and control those types of flow rates. And so that's what we are working on as a roadmap. In addition to that, we are also working on a metrology system, low flow metrology system that specializes in measuring extremely low flow. And right now, I would say that measuring anything below 1 SCCM, 1 skim, that is basically a few molecules, is a significant challenge in the industry. So we are working towards that. Overall, Brooks is committed to developing, mass flow controllers that are best in class, while we are attempting to meet the stringent requirements dictated by the advanced process nodes, and while focusing on reducing the cost of ownership.
Okay, well, that's very interesting. I appreciate your time today, Mohamed. Thank you.
All right. Thank you very much.